So we come to the session 8. So we are recalled all the definitions of ideals, subring, subgroup, subfield, and suitable examples. Now come to the ideals, left ideals. We already explained the left and right ideals, left and right ideals. Now, so a subset S of a ring R is said to be a left ideal of R. S is a subgroup of R with respect to additions. So if S is a subgroup of R under additions, the element of R to multiply the element of S in the left hand side. So this is called a left ideal. R belongs to R. R is a ring. So if you take a ring elements to multiplying a subset to left hand side, this is called a left ideal of R. For all, R belongs to R and S belongs to S. A non-empty subset S of a ring R is said to be a left ideal of R. S is a subgroup of R with respect to additions, and RS belongs to S. For all, R belongs to R and S belongs to S. This is called a left ideal. Now, in the same case, if you come to a non-empty subset S of a ring R is said to be a right ideal of R. So again, S is a subgroup of R under additions. So SR belongs to S. For all, SR belongs to R, and for all, S belongs to S. Yeah. Again, S is a subgroup of R under additions. Again, S is a subgroup of R under additions. So if we multiply an element of R to right side to the element of S, to multiply the element of R to multiply element of S on the right hand side. This is called a right ideals. Right ideals. For see, I give an example. Set Z equal to set of all. It is a minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. Suppose I take a subset of Z. What is subset of Z? Suppose I take a 3Z. 3Z. 3Z equal to set of all minus 9, minus 6, minus 3, 0, 3, 6, 9, etc. See here 3Z is S. Z is R. Suddenly S is a subset of R. S is an ideal. Ideal. You know the formula ideal. A belongs to R, B belongs to, then A minus B belongs to R. So A into B. So A plus R minus B. So A minus B belongs to R. So I feel like that. Under additions, A belongs to R, minus B belongs to R. A plus R minus B belongs to R. If you take S, yeah, subset A belongs to S, B belongs to S, minus B belongs to S, A plus R minus B belongs to S, suddenly A minus B belongs to S. It's an ideal. Similarly, if we take, so here R is a ring, S is a subset of R, means I take a 3Z is a subset. So 3Z is minus 9, minus 6, minus 3, 0, 3, 6, 9, etc. So S is a subgroup of R under additions. S is a subgroup of under addition. Okay. So I am multiplying. I take an elements of Z in form Z. So suppose if we take element 2, I am multiplying 3Z in 2. So we get minus 18, minus 12, minus 6, 0, 6, 12, 18. Suddenly is a subset of, again is an element of 3Z, is an again element of S, like that. So we are multiplying an element 3 in the left hand side is a left ideal. I am multiplying an element S in the element of Z in the right hand side is a called right ideals. So if S is an ideal of a ring R, then S is also subring of R. Obvious reason is that S is subgroup of R under additions. From the conditions, we have X is an element of R, X is an element of R, S is an element of S. The product X S belongs to S. So obvious X belongs to R. Now we come last. A non-empty subset S of a ring R is said to be an ideal if it is both left and right ideals. Both left and ideal. Simply say an ideal, either right or left ideal. Simply say an ideal. The ideal is subgroup of R and additions. And if we multiply in elements of R with element of S, we get product. It belongs to subgroup or subset. This is called it. Thus, a non-empty subset S of a ring R is said to be an ideal of R. S is a subgroup of R under additions. Rs belong to S or SR belong to S. For all belongs to R. For every S belongs to S. See, this is when we get an ideal definitions. So we come to the examples. So in the previous slide, I give a lot of examples. What's the difference between ideal, a subring, ideal, and a subring? So what is regarding the difference of ideals and a subring? The set of our integer is only subring, but not an ideal of a ring of rational numbers. Suppose if we take this set of integer is only a subring, but not an ideal of the ring of rational number. Suppose I take an example, the product of a rational number and integer. The product of a rational number and integer is not necessarily an integer. Suppose 3 belongs to Z, 3 is an integer. 2 by 5 is a rational number. I take a product 3 into 2 by 5. What's the product? 6 by 5. But 6 by 5 is not an Z, is integer, not an integer, but rationals. So I'm saying, so the product of a rational number and integer is not necessarily an integer. You take an example, 3 belongs to Z, 2 by 5 belongs to Q, but 2 by 5 into 3, the 6 by 5 does not belongs to Z. Therefore, Z is not an ideal of a ring of rational numbers. Keep it. Z is not an ideal of ring of rational number. You are choosing a ring is a rational number. Second examples, suppose this set of Q are rational. This set Q of rationals only subring, but not an ideal of ring of real number. Ring of real number. See, the product of rational number and real number is not necessarily a rationals. So the product of rational and real number is not necessarily a real number. For example, so for 1 by 2 into root 7 in R. Root 7 is a real number. If we take a product 1 by 2 into root 7, we get root 7 by 2. What's the root 7 by 2? Is a Q. In the Q is a rational. Therefore, Q is not an ideal of ring of real number. It's not a ring. You are choosing ideal in the real numbers. Therefore, Q is not ideal of ring of real numbers. See here, given a lot of yourself, you think, take a product, but if we take an integer, an ideal form, take a ring, whatever may be, either rational, either real. If you multiply, combine that. If you multiply means you take a product. What's the resultant? Either this or that. We get an idea. So what you are choosing, the product does not appear, but integer, the complex, are real, or rationals. Now, let R be any ring. Let R be a ring. S be a non-empty subset of R. Let R be any ring. S be a non-empty subset of R. So far as the operation of addition is concerned, whether S is a subgroup, whether S is a subring or ideal of R, S must be a subgroup of additive group of R. S is a subgroup for additive group of R. See, again, once again I repeat, see lesson. Let R be any ring, R be any ring, S be a non-empty subset of R. S be a non-empty, so S contains, simply as saying, S contains R. R is a ring. S be a non-empty subset of R. So, as for the operation of addition concerned, whether S is a subgroup of R, ideal of R, S is a subgroup, S is a subring or ideal of R, S must be a subgroup for additive group of R. I take an example. That's if I take I take A belongs to S, B belongs to S. Suddenly A minus B belongs to S means additive condition. A belongs to S, B belongs to S. Suddenly this implies minus B belongs to S. So A plus of minus B belongs to S means This implies A minus B belongs to yes. A minus B belongs to yes. But so far as the operation of multiplication is concerned, the previous is operation and concerned and the additions. If we come to the operation of multiplications concerned, for S to be a sibling of R, the product of any element of S must be remain in S. Product of any element of S must remain in S. Because suppose if A belongs to S, B belongs to S. I take any element R belongs to a ring R. R is an element belongs to R. Take Rn. I take a product. A into B belongs to S. A into B belongs to S. The product is also in S. AB belongs to S. This guy, on the other side of S to be ideal of R, the product of any element of R and any element of S must be remain in S. So I take R belongs to R, A belongs to S belongs to S, R belongs to R, S belongs to S. The product RS belongs to S. And similarly, SR belongs to S. Thus, an ideal required a stronger closure property for a multiplication than a subring. See, the ideal stronger closure property for the multiplication than a subring. In fact, every ideal is a subring, while subring may not be an ideal. This is understood. Every ideal is a subring. Ideal is a subring, but subring may not be an ideal. This is a stronger closure property. The stronger closure property is old in the ideals. So we are given a lot of example only regarding the set of integer. So integer is easy for understood. You are taking Z, take a subset of Z, so easy for understood. If you take a rational, if you take a real, it's very difficult. Difficult means not that. So one of the case, choose a real number is a subring. One of the case ideal in the case of rational. If you multiply, again a rational. Whatever you choosing the field of rational, whatever choosing the field of subring, whatever you choosing, be carefully observe. So that is the stronger or weaker, whatever maybe stronger closure property is old. Closure property is old in ideal form. So ideal is A not equal to 0, B not equal to 0, A minus B in S. So A plus of minus B, A minus B. The product is there. The stronger property is old. So the stronger is need a stronger is property old in the ideal form. For example, the set of integer only subring, but not an ideal of ring of rational. That's what I mean. The set of integer is subring, only a subring. Integer is concerned only a subring form, but not an ideal form. On the other hand, the set of every integer is a subring as well as an ideal of a ring of integer. These are needed examples, only the definitions for the ideals. What's an ideal? What's a subring? What's a subring? What's the difference of the ideal and the subring? We've given a lot of examples regarding ideals and subring. We get a totally understood the form of what's a form of subring, what's a form of ideals. So ideal is considered is a subring. So subring, but subring may not be an ideal form.